So today we're going to learn how to find the greatest common factor, also called the greatest common divisor, using the Euclidean algorithm. Now, if you can't recall what the greatest common factor or the greatest common divisor is, feel free to have a look at my earlier video where I explained this concept in great detail. Now, what is the Euclidean algorithm? The Euclidean algorithm is an algorithm that is roughly 2,300 years old and is an algorithm that was known to the ancient Greeks. So how were the ancient Greeks able to find the greatest common factor? I think this algorithm is best explained using an example. So let's say you wanted to find the greatest common factor for 336 and 105. So what is the greatest common factor for 336 and 105? It looks complicated enough, but according to the Euclidean algorithm, the way you would start is you would take the larger of these two numbers for which you want to find the greatest common factor. So you would take 336 because 336 is greater than 105. And you would just write it down. So you would write down 336. And now you're going to ask yourself, how many times can I fit the smaller of the two numbers in the larger number? So how many times can I fit this 105 in this 336? So how many times is 105 going to fit into 336? Well, can we fit 105 one time in 336? Of course we can, because 105 is less than 336. What about 2 times? Well, 2 times 105 is 210, and 210 is still less than 336, so we can fit 105 2 times in 336. What about 3 times? Well, 3 times 105 is equal to 315, and 315 is still less than 336. What about 4 times? Well, 4 times 105 is 420. 420 does not fit in 336, so we can't fit 105 4 times into 336. So the greatest number of times we can fit 105 in 336 is 3 times. Now, what is 336 minus 105 times 3? Well, 105 times 3 is 315, so 336 is equal to 105 times 3 plus 21, because 21 is what 336 minus 315 is. And remember, 105 times 3 is 315, so 336 is equal to 105 times 3 plus a remainder of 21. So what did we just do here? Well, we just asked ourselves, how many times can we fit the smaller number in the larger number, and what kind of remainder do we have left over? So we can fit the smaller number in the larger number 3 times, and then we'd have a remainder of 21 left over. And now what we're going to do is we're just going to take this number over here, this 105, and we're going to shift it to the left side of the equation. So we're going to shift it to the left-hand side. And we're going to take the remainder and we're going to put it in the place of 105. So what question are we going to ask ourselves now? Well, we're going to ask ourselves, how many 21s can we fit into 105. So how many 21s, how many of the remainders can we fit in the smaller value? In the smaller value for which we want to find the greatest common factor. And so 21 times 5 is exactly equal to 105. So the greatest number of 21s that we can fit in 105 is 5. And 21 times 5 is exactly equal to 105. So we're going to get a remainder of 0. 105 minus 21 times 5 is equal to 0. And once you get to 0 in this algorithm, all you have to do is you just have to look up to the previous line, the second last line, and look at the remainder from that line. So this 21, and this 21 is your greatest common factor, also known as your greatest common divisor, your GCD. Now it looks pretty complicated, so let's have a look at another example. So, what is the greatest common divisor of 143 and 528? Okay, what is the greatest common divisor of 143 and 528? Well, again, according to the Euclidean algorithm, take the larger of these two numbers, 528, and write it down. Then ask yourself, what is the maximum number of times I can fit 143, the smaller of the two numbers, in the larger of the two numbers, 528? Well, you can definitely fit one 143 into 528. What about 2? I'm going to do the math on the margin on the right here. So 2 times 143 is equal to 286. And 286 is still less than 528. So you can definitely fit 2 of them. What about 3? 3 times 143 is equal to 429, and 429 is still less than 528, so you can definitely fit 3 143s in 528. What about 4? Well, 4 times 143 is equal to 572, and 572 is now greater than 528, so you cannot fit 4 143s in 528. So the maximum number of 143s that you can fit in 528 is 3. So you're going to have 143 times 3. And now, what is the remainder that you're going to have? Well, it's going to be 528 minus 143 times 3, and 143 times 3 is equal to 429. So we can just do the math in our head. What is 528 minus 429? It's equal to 99. So that's the remainder that we're going to have. And now, take the smaller of the two values, so 143, and ask yourself, how many times can I fit the remainder in 143? Well, 99 is going to fit into 143 exactly one time. And 143 minus 99, again, we can just do the math in our heads, it's not very difficult, is equal to 44. And now do it again. Ask yourself how many 44s, how many remainders we can fit in the 99. So take the 99 and ask yourself how many 44s can we fit inside the 99. Well, 4 times 2 is 88, so we can fit 2 88s inside 99. 99 minus 88 is equal to 11, so you're going to have an 11 left over. And now do it again. Ask yourself how many 11s you can fit in 44. So you're going to get 44 is equal to 11 times what? Well, 11 times 4 is exactly equal to 44. So the maximum number of times you can fit 11 in 44 is 4 times, and you're going to get a remainder of 0. And once you get to a remainder of 0, just look one row up, and the remainder from one row up is your greatest common factor, or as some would call it, the greatest common divisor. Now, why does this method work? Why does this method for finding the greatest common factor or the greatest common divisor work? Well, I think it's easily illustrated in the previous example we had up here. So in this example, we just basically got to the greatest common factor in just 2 lines. So this is why I'm going to target it. Remember, we were trying to find the greatest common factor of 336 and 105. So let's target the first line over here. So 336 is equal to 105 times 3 plus 21. What is this telling you? What is this geometrically telling you? Well, what it's telling you is if you have an area of size 336, then this area is equal to some area that is divided into 3 105s. Let me do this roughly proportional. It's not going to be exactly proportional, but let's say it's equal to 105, 105, 105. So this is 105 times 3 over here, and then you have a remainder of 21 left over, right? So you can split 336 into 3 105s and have 21 left over. And this is coming from this line over here. Now, what is the second line telling you? What is the second line telling you? Well, the second line is telling you that you have some area. Let me draw a slightly larger area. You have some area the size of 105. And this area is equal to 21 times 5. So this area is equal to 21 times 5. 1, 2, 3, 4, 5. So every one of these smaller areas here is equal to 21. So think about what we're doing here. We're saying that 336, the larger of the two numbers for which we're trying to find the greatest common factor or the greatest common divisor, can be divided into 3 105s and a 21. And then we're saying that the 105 itself can be divided into 21s. So it's obvious that the 21 is going to divide 336. So it's obvious that 21 is going to divide 336 because 336 is divided into 21s and 3 105s, but every one of these 105s is in turn divisible into 5 21s. Every one of these 105s is divisible into 21s. So the 336 is divisible into 21s and 105s, and every one of the 105s is divisible into 21s. Therefore, 336 is divisible by 21. Now, what about 105, the second number? Well, the second number is just directly divisible by 21s. 105 is divisible by 5 21s in this particular example. Now, how do you know that this is the greatest common factor? How do you know that this is the greatest common factor? Well, think about it for a moment. 21 is not a prime number. 21 is equal to 3 times 7. So you could have divided 336 by 7, and you could have divided 105 by 7. Or you could have divided 336 by 3 and 105 by 3. But that would not yield the greatest common factor. That would just yield a common factor. The greatest common factor would be the product of these two other factors that you could have found, 3 and 7. So let's recap one more time what we're doing here. What the ancient Greeks realized is that if you have an area of size 336, you can ask yourself how many tiles of size 105 you can fit into this area of 336. And you can fit exactly 3 tiles of size 105 into this area of 336. And then you're going to have a small area of 21 left over. And now you're going to ask yourself, in the very next line, you're going to ask yourself, how many tiles of size 21 can I fit in this area of 105? And in this particular case, you can fit exactly 5 tiles of size 21 into this area of 105, and you're going to have no areas left over. Therefore, 21 must be a tile size that can completely cover both the smaller number 105 and the larger number 336, because a tile size of 21 can cover 105, but a tile size of 21 can also cover 336, because 336 is covered by a combination of tiles of 105 and 21 itself. So every one of these tiles of size 105 can be covered by tiles of size 21, and so 3 of these tiles of size 105 can all be replaced or covered entirely by tiles of 21. So these 3 tiles of 105 could in total be covered by 15 tiles of size 21, and then you have 1 additional tile of size 21, and that makes up 336. And so this is why the Euclidean algorithm, an algorithm that is roughly 2,300 years old, works in finding the greatest common factor, also known as the greatest common divisor.